Hello. Our today's lecture is about panel regressions or regression models estimated based on panel data. And before we proceed to the core topic, I would like to remind you very briefly regarding what panel data structure looks like. When you do cross-sectional analysis, you analyze n entities or n units, let's say regions, countries, or individuals, for one period. When you perform time series analysis, then you analyze one unit for t periods. And finally, when you do analysis based on panel data, you analyze n units for t periods. So on the left-hand side, you can find an example of balanced panel data set. By the way, this is how you should structure your panel dataset for designing a regression model in eViews, Gretel, or Stata. So we have entity 1 and entity 2. Each of them is analyzed for 6 periods, and there are no gaps in data. Basically, it implies that you can analyze two entities for the same number of periods. In contrast, on the right-hand side, you can find an example of unbalanced panel dataset. So as you can see, there is a gap for x2 corresponding to entity 1 period 3, which means that you cannot analyze entity 1 for period 3. In contrast, you can still do this in case of entity 2 because there are no gaps in data. So two entities will be analyzed for a different number of periods, and that's why this dataset is called unbalanced panel dataset. So there is at least one great advantage associated with using panel data because it allows you for analyzing the effects of both time variant and time invariant variables. Not always, of course, because in case of fixed effects model, you cannot include time invariant variables, but we are going to discuss it in the next video. So basically, time variant variables are variables which values change over time. So even if you analyze only one unit, let's say Poland, one country, then variables such as GDP, volume of trade, size of population will change over time. And time invariant variables do not change over time. They change only from one unit to other unit. They are different across units, but not across time periods. So the examples are geographical distance, common border dummy, and so on. Another advantage is that using panel data, you might collect a bigger number of observations, and this might be important because, as we discussed, you are more likely to obtain statistically significant coefficients if the number of observations in the sample is bigger. However, you shall also keep in mind that panel dataset might be more problematic than time series and cross-sectional data estimation. One of those complications is interpretation of unit root test for panel. So, when you perform unit root test for the panel dataset, the null hypothesis of the test states that all the panels, separate time series, have a unit root. And the alternative hypothesis states that at least one panel does not have a unit root. Intuitively, it's easy to see that even if you manage to reject zero hypothesis of the test, it does not guarantee that all the panels are stationary. Actually, you would have to analyze each panel separately. I will show you. So we use Gretel, we use straight balanced panel. As usual, you can find it in materials for this lecture. We use augmented Zicke-Fuller test with constant. Okay, so this is the output of the test. We have 6 units. because we analyze the volume of trade between Poland and 6 major trade partners for 22 years. So that's why we have output for 6 units. As you can see, for each of those units, we would fail to reject zero hypothesis about the presence of unit root, because p-value is significantly higher than 0.05. So this case is relatively simple. You can apply first differencing procedure, and you shall repeat until you obtain a stationary dataset. But you also have to keep in mind that all the variables have to be of the same level of integration. In our original model specification, we analyze how volume of trade depends on GDP and distance. That's why if you take the first difference of trade, you also have to take the first difference of the rest of variables. Except for distance, of course, because for distance it makes no sense. It would be just equal to 0, because distance is time invariant variable. So yeah, it means that all the variables should be of the same level of integration, or the same order of integration. Sometimes it's not desirable, to take the first difference. So in this case, if you have a relatively big number of units and only 1 or 2 have unit root, you might just exclude those units. So basically it's up to you. I would just say that differencing is more conservative option. Okay, so that was it when it comes to interpreting unit root test for panel data. And now I would like to proceed to 2 simplest model specifications for panel data. The first one is OLS. OLS basically ignores times and individual effects. So you can see that this equation was designed for panel data, and all the variables are time variant, so they change over time because we have I and T index, and they also change depending on the cross-sectional unit, again because of 2 indices. So let's say we analyze 10 countries for 10 years. And when you perform OLS model, you simply replace those indices with n. And n will take value from 1 to 100. So in other words, when you estimate panel dataset using OLS, you do not make any difference between difference in value of y for 2 countries analyzed for the same period and difference in y for 1 country analyzed for different periods. Basically, you just neglect it. However, I have to say that OLS is not the best specification for panel data, and we are going to discuss why in a second. So, before we do, we have to understand endogeneity and heterogeneity issue. Endogeneity is the correlation between independent variable and error term. And endogeneity is not consistent with OLS. OLS actually requires exogeneity. So you can recall the assumptions for OLS model we discussed before, and one of the assumptions states that there is no correlation between independent variable and error term. So if there is such a correlation, then OLS would not produce an efficient estimator. And unobserved heterogeneity is unobserved dependency of other variables hidden in the error term. Probably it looks very complicated, so let us discuss this based on our example. So imagine that you would like to analyze how the value of GDP depends on spending on education. which makes sense because spending on education increases human capital, which improves productivity and increases the volume of output. However, spending on education is determined by the hidden variable which is not included to this regression model. And this variable is the quality of governance or democracy index. Because democracy index is something what actually exists, and of course you can use it for your regression model. Democratic countries spend more on education. It's very intuitive, but at the same time many studies which examine the effects of democracy on economic growth report that this effect occurs through the channel of higher education spending. So that's why it makes sense. And that's why we know that spending on education and democracy index are correlated. However, because we omit this variable, the effect of democracy will be hidden in the error term. It will be here. So, due to the fact that effect of democracy will be hidden in the error term, it will be captured by the error term, we expect spending on education and error term to be correlated. So you might wonder why it's so bad, and this is why. So we know that there is positive correlation between spending on education and error term, because error term captures the effect of democracy, and democracy and spending on education are positively correlated. So first, we estimate effect of spending on education on GDP. So we know there is a positive causal relationship. However, we forgot to include the effect of democracy to this model. So democracy will affect spending on education, and spending on education will also affect GDP. So we overestimate the effect of spending on education. The estimated effect has a greater magnitude than true effect, and that's why our estimator is not efficient. So that's why endogeneity is not consistent with OLS estimation. Another thing is serial correlation of alpha. So even if you make sure that there is no endogeneity in the model, it's still very likely that alpha will be serially correlated. So value of alpha in period t would depend on the value of alpha in the previous period. And the reason for this is because GDP naturally increases over time regardless of the spending on education. So you remember that constant term or alpha or beta 0 is equal to the value of GDP if spending on education is equal to 0. So GDP will be equal to alpha plus error term. So if we do not account for other determinants of GDP, like capital stock or the size of the labor force, then probably we will end up with something like this. So alpha will be positively dependent on the value of alpha in the previous period. It will increase over time. So yeah, and there is nothing we can do about this. So of course you can try to ensure exogeneity by adding more variables, analyzing the correlation between variables and the error term. But when it comes to serial correlation of alpha, it's much more complicated. So that's why OLS is not the best option for you. So we can try to illustrate this issue by running OLS model for panel data. We estimate trade as the function of distance, GDP product, and we also add GDP per capita and European Union dummy. And here we are. So this is the output. And I'm almost sure that we will deal with heteroscedasticity and autocorrelation problems. So yeah, White's test for heteroscedasticity says that we shall reject zero hypothesis about constant variance of the error term, and autocorrelation test also indicates the presence of first-order autocorrelation. So yeah, this is just an illustration, of why OLS model is not the best option for panel dataset estimation. And another possible and relatively simple option is estimating between-model, which is perhaps the simplest panel model specification. So how do you technically estimate between-model? If we analyze 10 countries for 10 periods, then for each country you calculate the average value for the entire period. So if we have GDP of Poland for 10 years, then in order to obtain the average value of GDP for Poland, we calculate the average value of GDP across the years from 1 to 10. And we do it for all the units or the entities, all the groups in our model. So yes, in this case, of course, we completely neglect time variation. So we would be unable to assess the effect of increase in GDP or, let's say, productivity over time. We take averages and then we estimate the average values like a usual cross-sectional model. So this method is relatively primitive. As I told you, it will not allow you to assess time variation, the effect of time variation of variables, and probably you should have a relatively big number of groups in order to estimate the between model. So how you do this in Gretel? You click model, panel, between model, we estimate trade, and as you can see we end up only with 6 observations. So because we analyze the volume of international trade between Poland and 6 major trading partners, we have 6 groups for 22 years. When we calculate averages, we end up just with 6 groups. Okay, so that was it when it comes to panel data and using OLS and between estimation for panel data. In the next video, we are going to discuss more sophisticated specifications for panel estimations, and I really hope you enjoyed this one. Thank you.